Welcome, Sasha.
Thanks for having me.
Maybe we can start by discussing how the scaling laws came about in 2020 and 2022. What did those laws tell us about the behavior of deep neural networks and large language models?
So the main idea underlying a lot of the growth in language models has to do with that first L, large. And the largeness is not kind of just a fact of their existence. It's actually part of what makes them interesting as objects. Specifically, the idea is that as you put more data, as you put more size, as you put more resources in terms of computation into these models, they get better. And they get better in a manner that can be empirically measured and predicted. And in some sense, that property is what has allowed people to make the kind of long-term, high-scale investment in the technology. Both that it's like very good at what it does, but that it can become predictably better as you put in these resources. So in 2020, this paper kind of put out by OpenAI laid out this idea, and it laid it out in a series of very interesting graphs. The graphs show that if you start with roughly the same model architecture, you just increase along one of these axes, either the amount of data it was trained on, the size of the model, or kind of roughly speaking, the amount of money you put into the training process, that the models get better in a predictable way. And the kind of prediction was that if you could kind of know that this were true, really the kind of scientific process was more just scaling up the machinery around it. You can think of this akin to something like developing bigger rockets or developing larger factories to kind of synthesize materials, as have happened in other scientific disciplines. Now, as you say, this is purely an kind of empirical observation. We don't have any kind of particular theory for why this might work or what's really going on here. At least in 2020, we didn't. And so what's interesting about it is it's kind of really just a matter of plotting a bunch of lines on a graph and seeing where they head.
And what happened in 2022? There was another paper that came out and that just gave more details about what this might be like, these laws.
Yeah, the specifics of the difference between the paper in 2020 and 2022 are actually a little bit debated, and I don't want to kind of go into the specifics of them too much. What's interesting about the paper in 2022 is this is a paper from Google's DeepMind laboratory that goes by the name Chinchilla, is that they basically took very similar techniques from the 2020 paper. They used them in order to figure out kind of at very large scales where they thought the best resources for language modeling training should go. Specifically, they considered the amount of tokens and the amount of parameters, the size of language models. And they plotted a set of very interesting curves that kind of predicted over the next couple of years where they thought the best resources should go for training language models. In some sense, you can almost think of this as like a kind of economics law. We know that kind of computers will continue to get faster, and the same dollar will go to more compute on the output. And they were saying, well, what are we going to do in 3 years? What are we going to do in 5 years? Where along this curve will things be if we want to get the best usage out of that money as we go forward? And in some sense, once that was kind of written down on paper, they could then test that prediction by training very large models. Because we're only able to train these very large models 1 or 2 times, you really have to be relatively sure from your smaller runs kind of whether your model will be in the right regime.
So given that these laws were predicting the behavior of future models as you make them bigger and put, like you said, more money into and more resources into training them and building them, how seriously did the industry take this? And what impact did it have on the industry?
It's a fascinating question. I mean, as an academic, a lot of this stuff has become very serious trade secrets. So it's unclear exactly what the models that companies are training within their kind of walls. We do know that from things like GPT-4, even though the axes on the graphs were not really labeled, they did kind of claim they were still seeing performance improvements based on this same philosophy. We've also had models like Llama that have been released in last years or so that basically follow this structure. We can kind of know their details, and we know how they're getting better as they train to larger sizes. There are a couple kind of deviations from this formula that are important to know. One is that these formulas only tell you what to do if you want the best performing model. But there are often other axes that actually matter a lot in practice. So for example, these days, it doesn't matter that you have the best model. It often matters that you have a model that you can afford to deploy and utilize in practice. So there's a lot of interest in training somewhat smaller models that are nearly as good. And so when you have these kind of additional constraints, they kind of deviate from the formula of the scaling laws. But people have various other ways of doing them or ways of getting out those models that are not too different from how you train the biggest ones.
And in the past year or so, people have started arguing that these scaling efforts were saturating. Throwing more compute and more data at these models was not yielding the kinds of returns we saw just a few years earlier in terms of the behavior expected of models. Was that really true? And if so, what does that imply?
It's still another hotly debated topic. It's very hard to prove a negative that we've hit a wall from these kind of models. There are people like Ilya Sutskever, kind of a former lead researcher at OpenAI, who at our main conference of machine learning NeurIPS literally said that we've hit a wall and that we need kind of better ideas to get out of these processes. There are several things that could mean. One thing that people have noted is that we're simply kind of out of good data, that these models are now so large that they've kind of saturated the available kind of textual data that exists on the internet or in kind of any other ways you may get it. Kind of estimates these days are that there maybe only exists, say, 100 trillion accessible kind of tokens that anyone could get to in the world. And we've maybe just hit that point in practice. That being said, I don't think it's a clear answer that we've hit a wall. Talking to people at various labs, pre-training is still a big deal, and people are still thinking of other ways to make it bigger, to make it more efficient, and to get even better data. So I don't think it's a kind of clear, obvious scientific fact that we know that these curves have kind of stopped kind of working. It's all circumstantial from the fact that GPT-5 hasn't been released yet.
Right. Despite those concerns or lack of those concerns, something did shift in 2024 with the O1 series of models that OpenAI put out. They showed that they could do something different in terms of where to deploy the computing. They introduced this idea of test time or inference time compute. So can you talk a little bit about what that is and what that's telling us about how these large language models might be architected and used in the future?
For sure. So one way that people often talk about this is to think of language models as if they were kind of experts playing games. So if you're like a chess expert, you can study your entire life to be extremely good at chess, know all the possible moves, know everything that you could plausibly do. But still, in a game itself, if you have an extra hour to puzzle over the next move that you're going to make, you're going to do better. And that extra additional time for the specific given problem you're interested in can be really a huge difference. The analogy is similar here, that there's roughly two axes of a large language model. There's the time it can spend training, that's time before it even sees the problem at all. And then there's time it can spend actually kind of, quote, thinking about the problem. And this manifests itself in a kind of weird stream of consciousness where it gets to talk to itself about the problem in order to try to produce an answer. The kind of main breakthrough on this front that happened in 2024 was the release of the O1 series of models. These were a kind of series of models that OpenAI put out that have the ability to think for an arbitrarily long time in the process of answering a question. And what they showed was that given the ability to think for minutes or even hours at end, the model's performance would increase at a kind of regular and quantifiable rate. So they were able to kind of show that the model got better on the task they gave it by kind of thinking at test time. And arguably, this was the first time this was really demonstrated in a systematic manner.
And does this introduce a new set of scaling laws, even though we may not really know what those laws are yet, or they haven't been really written down?
Yeah, so they definitely made this claim, and they kind of showed that you have systematic scaling from this axis for these models. And other people have extended upon that. So just recently at their conference yesterday, Google released a new series of inference times chips with kind of the pure goal of trying to scale the inference time compute of their models. I do want to caution, though. I think OpenAI has every incentive to talk about this as kind of being a similar phenomena as what they did with training. But in terms of a product, it does look quite different than a standard language model. Standard language models are extremely general purpose. They can kind of do almost anything pretty well. And that scaling cost is a one-time cost that you pay for the training of the model itself. This test time compute so far has mainly focused on very specific technical problems. So in particular, it's very good at solving hard math problems and extremely hard coding problems when given a kind of correct environment. While there have been arguments that these skills may transfer to kind of other general purpose domains, I think it's not obvious yet that you get the same kind of free transfer that you got from kind of training models from scratch. So it continues to be a really hot and interesting area, but it's not exactly analogous to the original problem.
And earlier this year, we saw the release of DeepSeek R1, and we got to see some of the sort of quote unquote thinking that these models are doing at inference time. So what has been the impact of those models, particularly for academia, which suddenly has access to a pretty large model that they can, examine in more detail?
Yeah. Oh, wow. So I can talk for hours about DeepSeek. I find it an extremely interesting topic. And it's had a lot of repercussions, both in academia and in industry. Where should we start? So first off, I guess I should note that DeepSeek's important for two reasons. One is that they released a state-of-the-art base model, which is called DeepSeek V3. And they released it with a pretty permissive structure. So people are able to use it to start companies, to do research, to do all sorts of other things. The model is at the frontier in terms of its ability as just a base language model. And they also described a series of really interesting techniques they used for training the model, as well as releasing open source versions of the software and the kind of tools you need to run it. Frankly, it's awesome. And I was a little dismayed to see a lot of the kind of backlash against DeepSeek for it being kind of a Chinese company doing this. I really think it's an amazing scientific achievement and one that should be celebrated internationally, particularly at times now where it feels very tricky to kind of share resource back and forth between China and America. That being said, the question was specifically about R1, so let's talk about R1. So R1 was the second paper they released. You can think of it as an open source replication of OpenAI's O1 model. This R1 model is notable for its simplicity. The actual big scientific breakthrough in the R1 paper is just to show that something people thought was very hard was actually as simple as it could plausibly be. They demonstrated that basically by having a model guess the answers to math problems and then get feedback on whether those answers were correct or not, the model could learn not only to do better at math problems, but also to develop an ability to kind of meta reason, to kind of think to itself about the answers to the problem. So it could demonstrate that it would have this kind of thinking ability where it would talk to itself about the answer and do like a little bit of search in its own brain in a weird way in order to solve the problems. And you can induce this ability from relatively little compute in the scale of things. So that was a really exciting result. And the fact that they released that model, as well as smaller versions of the model, to the open source and research community was very important. So you ask kind of what people are thinking about in terms of these models. So there's a lot of research going into what the models are actually doing when they think. So the models will kind of talk to themselves. They'll kind of talk in a very weird and strange way. And eventually they'll arrive at an answer. A lot of people were really excited when language models came out because it was like the first kind of other thing in the world that could use language. Now we, in some sense, have the first other thing that can kind of like, I don't know, reason about problems. So it's just a very unique artifact.
Mm.
The other thing that there's a lot of interest in is other axes for inducing this sort of scaling behavior. So we've seen people work at kind of other ways of generating possible ideas for a problem. We've seen ways to use the internal structure of the model to do the thinking, so kind of avoid instantiating it in terms of actual text. And also a lot of work on just making these models faster and better and more useful for people.
So do you think the whole effort at scaling up test time, inference time, compute will keep going forward? People will find more and more new ways of using inference time compute for getting better behavior out of reasoning models?
It definitely seems like a hot topic. I think there's a lot of people working on it and thinking about it right now. I think that one thing that it particularly gets at is these kind of questions of the kind of core architectures of these systems. Like language models have, as kind of objects, remained relatively static for the last decade. We roughly came up with the idea for how they work and kind of just made them bigger and bigger and bigger throughout the years. This idea of thinking and thinking at test time may be the first thing that kind of motivates kind of rethinking the structure of these systems. Like if you know that most of the time you're going to spend is actually at runtime, you kind of would design them slightly different than systems that spend most of their time during training. And so the kind of economic trade-offs do shift with this new architecture.
And where is all this going? I'm referring specifically to the question that keeps coming up with the success of LLMs about artificial general intelligence. I know that the definition of AGI is very contentious. So assuming that we can all agree on some definition, will scaling alone, whether it's scaling up the training time compute or inference test time compute, will that alone get us to AGI? Or is something else needed?
So, I mean, with the caveat that I don't have access to a lot of information on this front, I think I am more bearish on the kind of promise of AGI in the next couple of years. The reason is that part of the story that a lot of people were telling when they were telling this story was that it was a story of scaling alone, that it was just obvious that we'd get GPT-5, GPT-6, GPT-7, and it would just be from kind of having a simple system and scaling it as we go. The fact that we haven't seen that and that there's a pivot for these new types of architectures means that there's a lot of variables still up in the air. There's a lot of kind of uncertainty about whether people will come up with new ideas or not. And because of that, I think it's like less obvious that I should just believe a couple of people who say AGI is coming. That being said, I mean, some of this reasoning stuff is pretty crazy. I think I've seen some stuff in the last year that I wouldn't have expected to see kind of at all, seeing them solve very hard problems, basically just from kind of looping on their own traces. And so that is a relatively new thing for me. So it doesn't make me think we've like totally stopped moving, but I think it's like a less clean story than it was probably 2 years ago.
Well, Sasha, I think that was a very good overview of how we came to the scaling laws and how we've come from the initial empirical discoveries of these laws to where we are now. Thank you very much for being on this episode of Polylogues.
Thanks for having me.